In this lesson, we'll look to apply much of the algebraic skills that we learned involving exponents and logs as we explore exponential and logistic growth models. To start, a haiku. Logs and exponents can offer us some advice. Start saving money. That haiku, of course, is referencing the discrete growth formula. If P is a principal investment or an initial amount, if we're thinking the context of money here, then imagine it's in dollars. And R is an interest rate as a decimal. So if you're talking about 3% per year, then that would be described as 0.03 in the formula. And T is time. Typically, this will be in years. Of course, though, it is dependent on our interest rate. If our interest rate is per year, then time is in years. And N is the number of times you compound that interest annually, then the amount that the investment will grow to, A, is equal to P times the quantity 1 plus R over N to the NT power. That's the formula right here. This idea of compound interest, all that means is to compound means to collect the interest you've earned up until that point. So you might collect your interest only once per year, and then the N in the formula is 1. Or you might collect the interest that you've earned up until that point twice per year, maybe halfway through the year and again at the end of the year. Often that would be referred to as semi-annually, and in that case, N would be equal to 2. So in the next couple examples, we'll see the effect of different values of N on the formula. Let's start with a simple example using simple interest. If you receive a gift of $1,000 on your 15th birthday and invest that money at a whopping 12% annual interest, how much would you have on your 65th birthday? And then a follow-up question, how long did it take your money to double? Try to answer these using the A equals P times 1 plus R over N to the NT formula while I pause the video. Sorry, you'll have to pause the video. I can't do that for you. For the first question, you'll find that you have over $289,000. To get this answer, simply evaluate A when T is equal to 50. The principal is 1,000, and the interest rate is 12%. As a decimal, that's 0.12. Number of compounding is just 1, and the exponent here is 50 times 1. So you'll find that you have over $289,000 on your 65th birthday. For the second question, you'll find that it took just over 6 years for your money to double. To work this out, we'll set A equal to $2,000. The principal is still 1,000, and the interest rate is still 0.12. Time is unknown, and the number of compoundings is still equal to 1. To start to solve this equation, I'll begin by dividing both sides by 1,000 to get this equation. And you'll note here that the doubling time, the amount it takes your money to double, is actually independent of the amount that you begin with. If instead I had started with $10,000, then I'd need to grow to $20,000, and after step 1, the ratio would still be 2. If I started with $100,000, it would need to grow to $200,000, and after step 1, the ratio would still be 2. Either way, I'd find that T is equal to the log, the base 2 of 1.12, or approximately 6.1 years. This reminds me of a handy rule from economics. The rule of 70, or rule of 72, as I've always called it. 72 is a bit nicer number. If you take the number 72 and divide it by your interest rate, instead of writing it as a decimal, keep it as a percentage, you'll find an approximate value for the doubling time. Many people use 72 instead of 70 because it's easier to divide 72 by rates of 2%, 3%, 4%, 6%, and come out with a nice even answer. Keep in mind that rule of 70, 72, either way, you're only getting an approximate answer, while the method that we used on the right gives you a more precise answer. In this example, let's look at the effect of compound interest. Essentially the same question. You received a gift of $1,000 on your 15th birthday. You invested at 12% annual interest, but now that interest is compounded monthly. That means every month you're going to collect the interest that you're due. So again, we'd like to use this formula A equals P times 1 plus R over N to the NT, but this time we have interest compounded monthly. Let's take a look at how that affects the answer. The most important thing to note is it means that N is equal to 12. If every month I'm going to demand the interest that I've earned up until that point be added into my account so that interest can earn interest, then that means I'm going to make that demand 12 times per year because it is annual interest compounded monthly. So the question, how much would you have on your 65th birthday, is calculated very similarly. Okay. But now I'll take my 12% interest as a decimal, divide it by 12, and I'll raise it to the 12 times 50th power. So a couple things to note here. The number that is being raised to the 12 times 50th power is 1.01. 1.01. 12 hundredths divided by 12 is only 1/100th. So that every time you're making that demand of give me the interest that I've earned, they're only giving you 1% every month. 12% a year, but only 1% every month. Meanwhile, since we're letting this investment grow for 50 years and there's 12 months in every year, there's 600 times that I'll be making this demand for the interest that I've earned. And in the end, I'll get 1,000 times 1.01 to the 600th power, which is actually a substantial difference in the total amount of my investment. Now I get $391,583 and about 40 cents. So nearly $100,000 more than in the last example. For the follow-up question, how long did it take your money to double? Remember, last time it took just a little bit over 6 years. So I don't want to use the rule of 72. It'll give me another approximation. So I'll say $2,000, the amount that the investment will grow to, is equal to $1,000 times 1 plus 12/100ths divided by 12. And I'll keep the N as 12, but now the T will be variable. So after one step, I'll get 2 is equal to 1.01 to the 12t, right? And now I'll have that 12t is equal to the log base 1.01 of 2. And that'll tell me that t is approximately equal to 5.8 years. So my money doubled a little bit faster, and then it doubled again a little bit faster. If it's doubling every 5.8 years for this first time, it'll double again in 5.8 years. And thus it grew to a substantially larger sum. This, of course, reminds me of a joke that also happens to be a haiku. I've heard it said money doesn't grow on trees, but banks have branches. Let's talk a bit more about this idea of compound interest. If you take $1 and you invest it at 100% interest, after 1 year, that $1 will grow to 2. That's the idea of discrete doubling. 1 goes to 2, 2 will go to 4, 4 will go to 8, and so on. However, if you take that dollar and you invest it at 100% interest compounded semi-annually, after 6 months, you will have $1.50. Right? You'll get that 50 cents, that half of the 100% interest that you've earned halfway through the term. And then that $1.50 will grow for another 6 months at 100% interest, and it'll grow to $2.25. You can confirm this with our formula. A equals P times 1 plus R over N to the NT. If we just let, say the principal equal 1, $1 here, our interest rate also equal 1 to represent 100%, and then our N, number of compounds, since it's semi-annually twice per year, that's going to be a 2, and then I'd have to raise it to the second power because N is 2 and T is 1. So $1.50 squared is $2.25. So you've got a little bit more than you would have if the interest weren't compounded semi-annually. If you didn't demand that you have the interest you've earned up until that point added into your account so that interest itself could gain interest. And this brings up a question. What is the limit of this idea of compounding? And this idea of a limit to the process of compound interest is such an important idea that we must introduce a new hero to our story, and that is Leonhard Euler. E is for Euler. It's pronounced like Euler, don't ever forget. You'll hear others often call him Euler like Bueller, but that's in fact wrong. Let me tell you a little bit about Leonhard Euler. Leonhard Euler, who lived in the 18th century, is one of the greatest mathematicians in history. He is also considered one of the most prolific, as all of his work fill over 92 volumes, more than anyone else in all of mathematics. He's actually so incredibly important that he has 2 numbers named after him. One of those numbers is the number E. E is the growth constant, and it represents the result of continuous doubling. So as we saw in the last example, when we look at a growth rate of 100%, when we have a growth rate of 100% and it's just compounded at the end of the year, you end up with 1 plus 1 over 1 to the first, and that's just 2. That's the idea of discrete doubling. But if we demand that that interest be collected halfway through the year, 6 months in, and then again, the rest of the interest that you've earned at the end of the next 6 months. So when we have an N of 2, instead of twice as much as our initial investment, we end up with 2.25 times as much as our initial investment. And we saw that in the last example, 1 plus 1 over 2 squared. When I evaluate 1 plus 1 over 4 to the 4th power, I get $2.44. So you see, each time it's a little bit more than our discrete idea of doubling. 1 grows to 2. Each time 1 is growing to a little more than 2. So we want to know, what is the limit of this expansion for n equals 12, as the example we saw with the large birthday gift. It will grow to $2.61. And when n is 52, so if you're collecting your interest every week, it would grow to $2.69. So as you can see in the table here, each time it's growing a little bit larger than 2, but the question is there a limit to this calculation? When n is 365, so you're in the bank each day demanding the small fraction of interest that you've earned up until that point, demanding that that be added into your account so that it too can grow with interest. At the end of the year, you'd end up with $2.71. And that is pretty much the limit of this process. E is defined, this number E, named after Euler, is the limit as n grows large of 1 plus 1 over n to the nth power. And E is approximately equal to 2.71. In fact, I could be a little more accurate. It's approximately equal to 2.71828. But that's not exact. E is a transcendental number like pi. And just like if somebody were to say, well, what is pi? You could answer more than saying pi is 3.14 or approximately 3.14. You could say pi is the ratio of the circumference to the diameter in any circle that you find. When someone asks you what is E, you could say E is a growth constant, and it represents the result of continuous doubling. And that's a very, very important idea, not only in finance. One thing this idea allows us to do is to switch our focus from discrete growth that happens every year or every 6 months or every set time period, to an idea of continuous growth, to allow an investment or a group of individuals, a population, to grow continuously. So you'll note the continuous growth formula here. The important thing to see is the similarity between the continuous growth formula and the discrete growth formula. For our discrete case, we said A of t is p times 1 plus r over n to the nt. And all I've done here was I've replaced 1 plus r over n to the n with e to the r, right? If e to the first is representing continuous doubling, r being 100%, then e to the r would be continuous growth at a growth rate of r. The natural question is, when would we use the continuous growth formula instead of the discrete growth formula? And as we'll see in our next few examples, sometimes it makes more sense to assume that a certain thing, maybe not an investment with money, but maybe something else, was growing continually. If you've taken chemistry, then this example might be familiar to you. Cobalt is a radioactive substance with a half-life of 10,000 years. A geologist finds a deposit of cobalt-121, which weighs 1.5 grams, and he estimates that the original deposit contained 20 grams. I'd like to know, how old is the deposit? Now, it seems to make sense that a radioactive substance wouldn't wait till the end of the year until it decays a little bit, and then wait again till another year passes before it decays a little bit. But instead, it would be decaying all the time. So I'm going to make an assumption that we can use our continuous formula, our continuous growth formula, even though it's used for decay in this case. So A is equal to PE to the RT. In this case, the P, the original deposit, is 20 grams. The amount that he found is 1.5. It's less because we're dealing with decay here. So E, and then the growth rate is not given at the moment, and the time is not given at the moment. So I'd like to solve this formula, and I'd like to know what T is. It seems I don't have enough information. However, I am given this piece of information. It has a half-life of 10,000 years. So that's kind of like the question I asked earlier about doubling. What we're told is it takes 10,000 years for this substance to get cut in half. It doesn't matter what the initial amount is. After this amount of years, 10,000, P will grow to half P. So after step 1, divide both sides by P, I'll get half. You see, again, it's independent of the initial amount. And this allows me to solve for R. And you see, once I know R, I can plug that back in to the first equation that I wrote and solve for T. Since these equations are base E, this is a job for natural log. So I can say 10,000 R is equal to the natural log, the log base E of 1/2. And that tells me that R is a very small number here, negative 0.0000069. This should have been a negative here. So you see that's a very, very small and negative growth rate. Negative is important because it's decaying, and the fact that the growth rate is so incredibly small, that's because we have a half-life of 10,000 years. It takes a tremendous amount of time for this substance to decay. Anyway, when I plug this R back into this formula here, and I solve for E, so here's the process that would be involved there. This would be E, I'll just keep writing it as R for simplicity. Then this would give me the natural log base E of 1.5 over 20 is 0.075. This would be equal to my growth rate times T. So if I divide both sides by my growth rate, I get T. And when I do all this, I find that T is equal to 37,370 years. Old. That's pretty old deposit. Another common application of our continuous growth formula would be for population growth, whether it's human population or some animal population. If we go back in time and look in 1940, the US had a very, very tiny, well, relatively tiny population of only 17 million. Belgian mathematician P.F. Verhulst was tasked with estimating the population in 1940 using data from the first 6 censuses. So there was a census done in 1790, and our population was just under 4 million. Another one in 1800, 1810, 1820, 1830, and 1840. We could try to do our own estimate of the population in 1940 and see how it compared to his estimate using our formula. So what I could do is I could pick off maybe 2 ordered pairs here. I'll choose the first one and the last one, but I could really pick any 2. And I could plug them into our formula here to get some idea of what the growth rate was during that time. So in 1790, let's say I let that be t equals 0. This is going to be t equals 0. And then in 1840, this would be t equals 50. And so if t equals 0 gives me a population of 3.929 million, then that means 3.929 million is, you can think of that as my initial population. And then if after 50 years transpire, my population is 17 million, I can think of that as the amount after some set amount of time, in fact, time 50. So as I plug this information in, I get 17.069 is equal to 3.929 e to the 50r, and I solve for r, I get a sense of what the growth rate is during this time. And I find that the growth rate is approximately 2.9%. So a little more accurate, it would be 0.029, let's say 4. So 2.94%. If I want to estimate the population in 1940 would give me what population, right? Then that's 150 years later. I'm going to use the same growth rate that we saw over the course of the first 50 years. And that'll tell me that the population in 1940 would be 3.929 e to the 150 number of years that have elapsed between 1790 and 1940 times 0.0294, which will give us a US population of 322 million people. 322 million 152,000 to be more exact. If we were to take a look and see how this compares to Verhulst's estimate, we'll see it's substantially different. In fact, Verhulst estimated a much smaller number of people in 1940, and his answer was, in fact, much more accurate. The model that he used was a logistic growth model. So a logistic growth model differs from an exponential growth model in a few ways. First, note the difference in the formula. A of t is equal to c divided by 1 plus b times e to the negative kt. Okay, so A is still representing the population or the amount after some amount of time. And K is still basically the growth rate. It's proportional to your growth rate. And T is still representing time, still usually in years. But B and C in this case are representing certain constants. To describe what these constants represent, let's take a look at a limit of A of t as time goes on to see exactly what Verhulst had up his sleeve when he made his estimate. If I look at the limit as t goes on, this grows larger and larger of this function A of t, then I'm evaluating this limit of c divided by 1 plus b e to the negative kt. So a negative exponent, of course, means a misplaced exponent that should be in the denominator. So I can rewrite this expression as c over 1 plus b over e to the kt. So let's take a look at what we have here. T is the amount that's growing large without bound. T is headed toward infinity, and it shows up in the exponent here. However, that exponential statement is occurring in the denominator under some constant b. It doesn't matter what that constant b is. That denominator is then going to grow large without bound. And no matter the value of b, this fraction here will head toward 0. And thus our limit of A of t, the amount that the population can grow to after an infinite amount of time, is simply c divided by 1 plus 0, which is just c. The constant c in this formula is often referred to as the carrying capacity. The carrying capacity implies some natural limit of the population. As the population can't grow without bound, always doubling and doubling again, but instead there's some limit that it can't surpass, because as it approaches that number, the group of people or the population that you started with, they start to run out of resources, they start to run out of space, and their population has a ceiling on it. And that's what the carrying capacity is all about. And that's what Verhulst used when he was estimating the population in 1940. Remember, he was way back here in 1840. This is the actual data we're looking at here. And he put a certain ceiling. He said, I don't think the US population is going to grow beyond this ceiling. It might have been, I don't know, 170 million or something like that. He said, as we start to approach that 170 million, our exponential growth that we're exhibiting now is going to start to level off and become asymptotic, if you will. And thus that gave him a population estimate in 1940 of closer to 140 million, which turned out to be much more accurate, at least much more accurate than our estimate using the exponential growth model of 320 million. However, when you look at his model, the red curve here, with the actual data going to 1940 and then beyond, you start to see the reason that he hit the mark wasn't necessarily that we started to reach this carrying capacity, but instead you're seeing the effect of the World War, notably World War II, that started to level off the population for only a brief moment in time. And then you later saw our population start to grow exponentially again, closer to a growth rate of 2.9% coming out of the 1940s into the 1950s and 60s. We'll look at an example involving this logistic growth model. So we're going to suppose that the growth rate of a population can be modeled with a logistic curve, and it's given to us right here. So P of t is our population after time t is equal to 20,000 divided by 40 plus 460 e to the negative 0.12 t. So remember, these different constants all play an important role in the growth. Our question is, will this population be able to grow to 10 times its current size? And if so, how long will it take? So to answer this question, there's a few things that we need to know. If we're asked, will it be able to grow to 10 times its current size, we'll have to know, what is its current size? What is P sub 0? And we'll have to be able to compare that to the carrying capacity. Is P sub 0 times 10, which is 10 times its current size, is that greater than the carrying capacity? Because if it is greater than the carrying capacity, it won't, at least not according to the logistic curve. It won't pass that upper limit. And so let's find out. P sub 0, when I plug in 0, I just get 20,000 in the numerator, and I get 40 plus 460 e to the negative 0.12. Oh, that's just going to go to the 0 power because t is 0. And so I have 20,000 divided by 40 plus 460. That's 500. So it looks like our initial population is 40. Okay. So what I want to know is, will this population be able to grow to 10 times 40? 10 times 40 is 400. And, well, the carrying capacity, I don't have to do a whole lot of work for the carrying capacity. The carrying capacity right here is 20,000. So if you want to think about this visually, right now we're at a population of 40, right? I'm asked, can it grow to a population of 400? And the answer is yes, because the carrying capacity is 20,000. That means we're not going to see things level off until we get to 20,000. So yeah, we'll be able to grow to 10 times its size and substantially more than that. So now I'm ready for the second part of the question. If so, how long will it take? This is just a matter of setting P equal to 400. 400 will equal 20,000 divided by 40 plus 460 e to the negative 0.12 t, and solve this equation for t. First step, I'll multiply both sides by that denominator, 40 plus 460 e to the negative 0.12 t, and I'll also divide both sides by 400. So on the right-hand side here, I'll have 20,000 divided by 400, which would be 50. I would subtract 40 from both sides, and I get 460 e to the negative 0.12 t is equal to 10. I would divide both sides here by 460 and get 1/46. And then I'd just do a little log work that we grew so accustomed to doing. Negative 0.12 t is going to equal the natural log of 1/46. All right, and then I'll solve for t. The natural log of 1/46 divided by negative 12/100 is about 32. So this will take about 32 years to grow to 10 times its size. Wrap things up here with the big idea. We can use all the stuff that we learned about solving logarithmic and exponential equations to come up with some really important models for growth. We have continuous and discrete growth that can both be modeled with exponential equations. But we also have this idea that, well, in haiku form, exponential growth assumes endless resources, and that's not practical. So we can put a limit, a ceiling, if you will, on the exponential growth and come up with a new model, a logistic model, a model that starts off growing exponentially until it hits a certain inflection point, a point where things start to change, resources become scarce, space becomes scarce, and things start to taper off and never go beyond some carrying capacity.